Welcome to the 37th lecture of the MOOC on parallel algorithms. Today we shall show that the max flow problem is P-complete for NC reductions. You must be familiar with the max flow problem. In a max flow problem we are given a flow network. A flow network is a graph with a set of vertices and directed edges and with two designated nodes S and T, and then every edge in the graph has got a capacity, and we have to define a flow so that the net flow out of the source, which is equal to the net flow into the sink, is maximized. So the decision version of the problem is what we consider today. Here we have to answer questions of this sort given a network and a flow value. Check if this is the maximum flow the network can have. So we shall show that the max flow problem P complete for NC reductions by showing that the max flow problem is at least as hard from the perspective of NC reductions to MCVP2. MCVP2 is a short form for monotone CVP for fan out 2. A monotone Boolean circuit uses AND OR gates but no NOT gate. So what we have to check is this: in a monotone CVP problem, an MCVP2 problem, we have to check this given a monotone circuit, a circuit that uses only AND OR gates, in which the fan out of every node, the fan out of every gate is less than or equal to 2. So given such a circuit, check if it evaluates to 1. This is the monotone CVP2 problem. It can be shown that even though monotone CVP2 is a restricted variant of CVP, this is at least as hard as the CVP problem from the perspective of NC reductions. I'll leave the reduction as an exercise to you. I'll give you a hint nevertheless. Recall the proof that CVP is P-complete for NC reductions. Get rid of negation from the circuit constructed there. Recall the proof that CVP is P-complete for NC reductions. In that proof we assumed, we considered a language L, an arbitrary language L belonging to P. Since L belongs to P, there is a deterministic Turing machine that is polynomial time bounded for deciding L. We took the transition table of this Turing machine and used it to construct a circuit. In this circuit we had used NOT gates in one place. See how you can get rid of the use of the NOT gate here. That is, you have to replace this NOT gate with and OR gates, and then you have to ensure that every gate that is used has a fan out of 2. Once you do that, you would have reduced the CVP problem to MCVP2 problem. Therefore, we can show that MCVP2 is P-complete for NC reductions. It is this proof that we are going to depend on now. So we assume that we are given an instance of MCVP2 in NC. We can construct a flow network which will have an odd flow, an odd maximum flow, if and only if the circuit evaluates to 1. We of course know that max flow belongs to P. You would have studied a polynomial time algorithm for finding the max flow of a flow network in the first algorithms course. So that establishes that max flow belongs to P. So this is the first part of the proof. The second part of the proof will show that MCVP2 NC reduces to max flow. When you combine these two parts, we would have established that max flow is P-complete. So now let us prove the second part. So we are given an instance of MCVP2. Let this instance be represented like this. We are numbering the gates from the other end. So the last gate will be now numbered G0. In this, each Gi is an input. 0 or 1, or it is the AND of Gj and Gk, where j and k are greater than I. Since the numbering is now from the other end, the input side is numbered higher. In every AND operation, the inputs will have larger numbers than the output, or it is Gj or Gk, where again j and k are greater than I. So we are given such a circuit, and the requirement is to evaluate G0. That is, we have to check whether G0 evaluates to 1 or not. So that is the MCVP2 problem. Now given this instance of MCVP2, what we are going to do is to construct a graph, a flow network, using the inputs of the MCVP2 circuit. So in the flow network, every gate becomes a vertex, and there are two extra vertices named S and T. These will function as the source and the destination of the flow network, and then we place edges. Now what are the edges like? Every connection in the circuit is an edge. There is a connection from S to every input gate or an input value. Every S will be connected to every input. So this is an edge which is directed from S to I when Gi is an input. And then there is an extra vertex T. Every AND gate has a directed edge into T, and every OR gate has a directed edge into S. And finally, we have an edge from node 0, which corresponds to G0. So these are the directed edges. Of course, there are some more edges. Every input Gi has a directed edge. So these will form the set of edges of the graph. So let us take an example. Let us say we are given this circuit. G0 is an OR gate. This has two inputs. One input is the output of G1. G1 is an AND gate. And the other input is the output of G2, which is also an AND gate. G4 is an input. There is an OR gate G3, the output of which will drive an input of G1 and G2 each. So here G4, G5, G6 and G7 are inputs. They have values 1, 1, 0 and 0 respectively. So let this be 0. So this is the circuit that we are given, let us say. Then what we do is this. For gates 1 and 2, we take vertices like this. This is vertex 0. We have directed edges from 1 to 0 and 2 to 0. These are, of course, the circuit edges. There is a directed edge from 1 to 0 and 2 to 0. Similarly, we replicate the circuit. This is G4. These are the outputs of G3. The inputs to G3 are from 5 and 6 respectively, and the inputs to 2 are from 3 and 7. And then we have a new vertex S and a new vertex T, and we have connections of this sort. From 0 we have a connection to T. From 1 we have a connection to T, that's because 1 is an AND gate. Similarly, from 2 also we have a connection to T, that's because 2 is an AND gate. S is connected to 4, 5 and 6 and 7. These are the input values. And we have edges from 3 to S. 3 is an OR gate. So we have an edge from 3 to S, and we also have an edge from 0 to S. So this is the flow network that we have. But of course, for the flow network to complete, we also should specify a capacity for the edges. Of course, some edges have not been drawn here. We are going to have edges from 4, 5, 6 and 7 back to S. Those edges are not drawn here. Let me draw them now. These are edges going back from the input nodes to S. So this will complete the flow network n equal to VA. A is the set of all the edges here. Now let us specify the capacities of the various edges. For an input Gi, capacity of Si is defined as 2 power I if Gi equal to 1, 0 otherwise, and the capacity of Cis is defined as 2 power I. Coming back to this figure, therefore, the capacity of the edge from S to 4 will be 2 power 4. That's because this node is numbered 4, and the capacity of the edge from S to 5 will be 2 power 5. The capacity of the edge from S to 6 will be 0. That's because 6 is an input 0, and the capacity of the edge from S to 7 is also going to be 0. And the backward capacities are all going to be 2 power 4, 2 power 5, 2 power 6 and 2 power 7 respectively. So that is what we have said. CSI is 2 power I if Gi equal to 0, Gi equal to 1, 0 otherwise, and CIS is 2 power I irrespective of the value of the input. And then for an AND gate, Gi, that is Gj into Gk, we define Cji as 2 power j, Cki as 2 power k, and Cit as 2 power j plus 2 power k minus d into 2 power I, where d is the fan out of Gi. So this is the second case. For every AND gate, we define the capacities of the involved edges in this manner. So going back to our figure, the AND gates here are G1 and G2. So capacities for G1 and G2 will be defined in this manner. G1 has a capacity of 2 power 1 and a capacity of 2 power 2 on these edges. That is, the outgoing edge of G2 will have a capacity of 2 power 2, and CIT would be 1 and 2 are the AND gates here. Therefore, for the incoming edges, the capacities would be 2 power 4 here, 2 power 3 here. For this gate, the J and K values are 4 and 3 respectively. So the capacities on those edges would be 2 power 4 and 2 power 3. Here for gate 2, the capacities would be 2 power 3 and 2 power 7. So these are the incoming edges into the AND gate. And for the edge from I to T, the capacity is going to be 2 power j plus 2 power k minus d into 2 power I. Here for gate 1, d is 1, it's driving only the input to gate 0. Therefore, the capacity here is going to be 16 plus 8, 24 minus 1 into 2, which is 22. Whereas for gate 2, the capacity, the incoming capacity is 8 plus 128, which is 136, and there is only one input being driven by the output of gate 2, which is that of gate 0. Therefore, d equal to 1 for gate 2. So d into 2 power 2 is 4. So 136 minus 4 is 132. So the capacities of the edges involved with AND gates are marked thus. Then for the OR gates, if Gi is an OR gate with Jk greater than I, then the capacities are defined like this. Cji is 2 power j and Ckj, Ki is 2 power k. These are exactly as in the case of the AND gates, but now we have an edge back into the sink. The capacity of this edge is going to be 2 power j plus 2 power k minus d into 2 power I. And finally, we define the capacity of Z0t to be 1. So marking these capacities in the figure, we have to consider the OR gates. So which are the OR gates here? 3 is an OR gate and 0 is an OR gate. So when you consider 3, its incoming edges have capacities of 2 power 5 and 2 power 6 respectively, and the outgoing edges as have been marked have capacities 2 power 8 and 2 power 8 respectively. Therefore, the edge which is going back from 3 to S has a capacity of 80. 2 power 5 plus 2 power 6 minus 2 into 2 power 3 is 80. That is the capacity of the edge from 3 to S. Now coming to vertex 0, these edges have capacities of 2 power 1 and 2 power 2. The edges from 1 to 0 and 2 to 0 have capacities of 2 power 1 and 2 power 2 respectively. And according to the fourth clause, the edge from 0 to T has a capacity of 0. And according to clause 3, the edge from 0 to S has a capacity of 5. Now the capacity of every edge is marked except the green edges that are from the inputs to the source. For these edges, the capacity would be 2 power the ordinal value of the input. So for the edge from 4 to S, the capacity would be 2 power 4, and the edge from 7 to S will have a capacity of 128. So this is how we assign the capacities. So this is a flow network. Now once the capacities are assigned, we define a function flow f. After defining the function f, we shall claim that f is a flow and shall show that it is in particular a max flow. So we define flows in this manner. For an input gi, f of Si is defined as C of Si. So all the edges from S to I are saturated. For any ij belonging to the network where neither I nor j is S or T, we define f of ij as 2 power I if gi evaluates to 1, 0 otherwise. So in step 2, we are considering the edges that are in fact edges of the network. Every network edge, every network connection became an edge in the graph. And these are the edges that do not involve S or T. For these edges, we define the flow in this manner. For an edge that is from I to j, so this is from the output of gate I to an input of gate j. For this edge, we define the flow as 2 power I if gi evaluates to 1. Otherwise, the flow is defined as 0, f is 0. Now let us come to the edges that involve S or T. For gi equals gj and gk, an AND gate where j and k are greater than I, we define fit as cit if gi equal to 1, fit as f of ji plus f of ki otherwise. So here we consider all the edges that are from the AND gates to the sink T. Similarly, let us consider the OR gates. We define f of is, the flow back into S, as f of j plus I, f of ji plus f of ki minus d into 2 power I if gi equal to 1, equal to 0 otherwise, where d, as before, is the fan out of the node. And finally, we define f of 0t as 1 if gi equal to 1, as 0 otherwise. So this is the definition of a function. So we have defined a function f in this manner. Now we claim that f is a flow. For f to be a flow, it should satisfy 3 conditions. One is the capacity constraint. The capacity constraint says that the flow from I to j for every edge ij must be less than the capacity of the edge, less than or equal to the capacity of the edge. Then the requirement is that of skew symmetry, which says that the flow from I to j is the negative of the flow from j to I. And finally, the third condition is that of flow conservation. That is the net flow into a vertex. So when these conditions are satisfied, we say that f is a flow. Now you can easily verify that these conditions are satisfied. Compare the capacity function that we defined earlier and the flow function that we have now. We find that on every edge, the flow that we have defined is less than or equal to the capacity of the edge. Some of the edges are saturated. For example, the edges from the source vertex S to the input signals, these are all saturated, but some edges are not. But everywhere, the flow that we have defined is less than or equal to the capacity. So the capacity constraint is satisfied. And then you can verify that the flow conservation is satisfied everywhere, and the way we have defined the flow skew symmetry is also satisfied. So talking about the flow conservation, we can look at a few examples. Consider a gate Gi. Let us say this is an AND gate. Let us say it has inputs from Gj and Gk, where j and k are greater than I. Let us say both Gj and Gk evaluate to 1. If both of them evaluate to 1, then they would be putting out flows of 2 power j and 2 power k on these edges. So the total incoming flow into Gi is 2 power j plus 2 power k. And let us say Gi drives two inputs. Since Gi evaluates to 1 here, on these edges it would be putting out a flow of 2 power I each. So the net inflow is 2 power j plus 2 power k, and the net outflow is 2 power I plus 1. And the edge that is from Gi to T is going to get 2 power j plus 2 power k minus d into 2 power I. So we find that all these edges are saturated when Gi is an OR gate with two input signals, both are 1. And the flow conservation is met. D is 2 here because this gate drives two inputs. So every edge is saturated. Instead, if Gi were an AND gate with 1 0 input and 1 1 input, that is, let us say Gk evaluates to 1, but Gj evaluates to 0. Therefore, the flow put out by Gj on this line is going to be 0. Therefore, the total inflow is 2 power k. Since the gate evaluates to 0, it would put out 0 on both the outgoing edges, but the edge to T will have 2 power k, thereby maintaining the flow conservation. So as you can see here, f of it is f of ji plus f of ki, the net inflow into the gate when the gate evaluates to 0. Another example, consider an OR gate. Let us say Gi is an OR gate with both inputs 1, and let us say it drives one input. On that input it puts out a flow of 2 power I. Then on the edge which is going back to S, it would put out 2 power j plus 2 power k minus 2 power I, the net inflow minus the outflow. So again, flow conservation is satisfied. So likewise, you can work out all the cases and show that flow conservation is, therefore f is a flow, f is a flow function. Next we claim that f is a max flow. We know that a flow function f is a max flow in a flow network N if and only if the flow network doesn't have an augmenting path with respect to this flow. So there should be no augmenting path in N equal to EA with respect to the flow function f. If f is a max flow, this is how it is going to be. So let us assume the contrary. Assume that there is an augmenting path, AP for augmenting path. So we assume that there is an augmenting path. Now when you look at the graph, we find that all edges of the form Si are saturated. If an input is of value 0, then it has a capacity, the Si has a capacity of 0 and the flow on it is 0 as well. If the input has a value of 1, then the capacity is 2 power I and the flow on it is also 2 power I. So all these edges are saturated. Therefore, the augmenting path starts with the backward edge. Now when you look at the other end, T has no outgoing edge. Now an augmenting path is a path of the underlying undirected graph of the flow network, and this path is from S to T, and since T has no outgoing edge, we are sure that the last edge which is used by this path is a forward edge. What we have just now established is that the first edge is a backward edge. Therefore, in this path we are beginning with a backward edge and then ending with a forward edge. So there must be a pair of consecutive edges somewhere where the first one is backward and the second one is forward. Since we are beginning with a backward edge and ending with a forward edge, at some point we should be switching from backward edges to a forward edge. So let us pick out one such case. Let us say the vertices involved are j, I and k. So we have backward edge from j to I In the augmenting path, we have an edge from j to I, which is a backward edge, which means the network in fact has an edge from I to j and a forward edge from I to k. Now, this is an augmenting path, which means f of ij is greater than 0. The actual flow is from I to j. So, we would be pushing more flow along this path by reducing the flow from I to j. On the other hand, since ik is a forward edge and is a part of the augmenting path, we have that its flow Fik is less than Cik. This edge is unsaturated, so it is possible to push more flow along this path. In total, when you push more flow from j to k, what you do is this: you reduce the flow from I to j. There is an existing flow from I to j which we reduce, and then we push more flow from I to k. More real flow is pushed from I to k. That is how we manage to increase the traffic from j to k. So, what we know is that there exists vertices I, j, k, where in the augmenting path they appear in the sequence j, I, k, so that this condition is satisfied. So, now let us see what this entails. This breaks down into 3 cases. If Gi happens to be an input, then j equal to s. The only incoming edge into an input vertex is from s. But then every edge from s to I for an input I is saturated. In other words, or we know that the edge from I to s has a flow of 0. This is a contradiction, because what we want is that f of ij is greater than 0. So, if Gi is not an input, then Gi must be an AND gate. So, ij and ik are the edges going out of this AND gate, and we assume that j is not equal to t, because in the augmenting path which is directed from s to t, j is on the side of s. So, j is not equal to t. So, Gi is an input to Gj. F of ij is greater than 0 means that f of ij is 2 power I. It can have only 2 values, 0 and 2 power I. So, in this case it is 2 power I, which means that Gi evaluates to 1, that is when f of ij is 2 power I. If Gi evaluates to 1, then f of ik equal to C of ik from the definition of the flows, whether k equal to t or not, which means the edge ik is saturated. But that is what we explicitly assumed otherwise. We assume that f of ik is less than C of ik. So, this is a contradiction again. So, in this case also we get a contradiction. Finally, in the third case, when Gi is an OR gate, we see that f is either 0 on all arcs from Gi, that is when Gi evaluates to 0, or all arcs from Gi are saturated, as we saw earlier, except possibly Is. Now, k is not equal to s, because k is on the side of t in the augmenting path, and f of ik is less than C of ik. Thus, we explicitly assumed that the edge ik is unsaturated, but then this means that f of ij has to be 0, which is a contradiction again, because the other assumption that we made is that f of ij is greater than 0. So, either way we get a contradiction. That is, once you assume that there is an augmenting path in the flow network, there is a contradiction, which means there is no augmenting path. And if there is no augmenting path, then f is the max flow. Now, if you look at f, you find that every flow of an edge, that is the f value for every single edge, is even except possibly for the edge 0t. F of 0t could be 1 or 0, every other flow is a power of 2 or 0. Therefore, the net flow is odd, the value of the flow is odd if and only if f of 0t is 1. But then when is f of 0t 1? F of 0t is 1 if and only if G0 evaluates to 1, or in other words, the given circuit evaluates to 1 if and only if the max flow of the network that we constructed is odd. Now, we can easily see that the construction of the network is done in NC. That is because to construct the network, all that we have to do is to take the circuit, create one vertex for every single gate, create the new vertices SNT, and then connect up and define the capacities. This can all be done in NC. Therefore, putting it all together, now we have shown that the max flow problem is P-complete for NC reductions. That is it from this lecture. Thank you.